Our next speaker, who's already introduced the event earlier, is Rupert Maleczek. He's an architect, researcher, and digital consultant, currently working as a postdoctoral senior scientist at the Institute of Structure and Design at the University of Innsbruck. And in his multidisciplinary work, he explores the relationship among geometry, form, structure, performance, materiality, and both digital and physical production. And he also likes to build big things, of which he will, I think, show us some.
So I guess I changed the title to as a facade or a beam. We try in Innsbruck, together with some industry partners, to develop in that direction. And maybe just to make my background a bit clear, so I'm very interested in this area of research and practice and teaching. So it's an overlap of everything, a little bit probably like the origami gathering. Basically, I guess it's very important to say, so everything I do, it's like depending on a lot of people. So sorry if you're not on the list, then I forgot you, but maybe someone is in the room who is interested in that. So why is that so interesting? I probably hope it's not starting automatically. I guess folding as a fabrication process, this is really fantastic, and it's fast. We got a lot of materials in the industry that come from flat sheets, and we heard a lot about crease pattern and folding. And of course, if you try to scale these things up, then you have to simplify and reduce the complexity enormously, so you can build beams or other stuff. This is one of the first beams we built. It's kind of folding inspired, I would say, but it's not folded. I showed this later. Of course, in this journey of scaling up things, we did some experiments in paper. So this is like a 7-meter spanning paper pavilion, or even just recently, just working with inflation together with Georg Kummer. So there's a lot of people, Yibei, Tomohiro, there in the room. We could develop ways to interpret foldable surfaces with different materials. Today, I would like to give you a little journey about trying to fold wood, so get from paper to plates to structures, how this can work. And so this shows already the idea. So you have this paper model that probably every architect and engineer knows from the model making process. And I'm really fascinated that this kind of works in wood. So if you go for a more complex pattern, maybe this one is a quite known one. It's the lens tessellation. There's a very interesting paper. Of course, Eric Demain is involved, Tomohiro is involved, Dux, Koschitz is involved. So what we did is, of course, as we are not these mathematicians, as you heard before, we developed the method to kind of get very close to a proper result, and knowing as an architect that the first thing you learn in architecture school is like you have to know about deviations. So if it fits almost, you have already a very good result. We built this in paper, and the question was, can this be done in wood? And if yes, how would that work? And so we designed based on a very simple design surface, these lenses, and we thought originally that folding wood might be very difficult. So maybe using the developable surface as an idea to just assemble things. And we thought this works quite nicely with these teeth. And originally, if you have a straight line and then these teeth, they slide into each other. The problem is when you bend it, you have to pre-bend it first and then put them together. So this is quite a difficult process, but as you can see, it works. You can easily put the things together and they hold. You can get the stable structure, but still, it's not yet folding. It's only taking the advantage of you can fabricate it flat, but not really assemble it flat. So as a first iteration, we tried to learn what could be a good substitute for a hinge. And in a very simple way, we just glued a big piece of fabric on it and thought maybe this is a very good solution. But of course, if you work with wood, so it might be difficult to learn if this is a valid solution. So today we heard a lot of things about tuck folds, so taking away material or hide it, as you have seen in these diagrams from Tomohiro Tachi's lecture. So as an architect, you also can say, well, if it's behind the surface, maybe it's not necessary, and we can simplify the process. So we can get rid of parts that are not used, but then I have some sort of a slit, and maybe this is so simple that it can work out for us. Then again, for a textile hinge, you kind of need to learn where to put this hinge. So basically, if it's depending on the fold direction, it makes sense you can let it open, or you better pack it inside so it's get a smoother motion. And so during the things, there is some parts, as you can see, where we just glued it. So in the middle part, we just glued the textile directly on it. And on the side parts, we packed it in between two layers of material. And then comes the first problem. So we have this one, and you see there's like these wooden parts blocking the hinges, because you have the following problem, that if you have a classical origami, so if I have, for example, this one, then the instruction will tell you just rotate it 180 degrees. If you have a sheet like this becomes already a bit of a problem. So you start to need to use a crane. But what is very interesting, by just using gravity, so we just take the right points to lift it up, you can just fold a structure that you can just lay out in a flat place. And if you look carefully, what is very interesting, usually on construction sites, you have someone with a tape measure or some way to kind of control, is it in the correct position? Here, we just closed the slits and we knew this is the perfect position. I don't know if the coffee break is on. However, you could do that, but like it was still not the speed that we were expecting, because like there is a lot of things you need to kind of manually access. There's a lot of people that run around. So inspired by this wonderful tent that probably everyone knows, you just throw it away. So even distribution of work, there's one person working, there's two already having a break. So we thought this might be a very good idea to do so. And so the idea was to find a way that folding can adapt this and make it speed. And so we made a very simple idea. So you have a rectangular piece, and by just pushing the sides, you can have a ready beam that can be used. And so from a folding perspective, it's quite simple. So you can have one rigid foldable element that you close to a tube. And if you add two straight fold lines, so these are the lines here, then it becomes a non-rigid snapping element. And you can even tune by the side. So if you come later for the washa, you will see there's one that's written inward. So this is not fully developable, but it snaps harder. So it has more stability, more resistance. So you can tune the stability of your beam. So if you fold something that is thicker than a piece of paper, you have like the red line that gets shorter and the blue line gets longer. So you have a lot of friction happening like that, and a lot of tensions. So you kind of need to adapt the fold lines as such. So what we did is like we tried to straighten them out in the end and tried to see what is happening really when you try to snap it. And so what is happening is that you see that this straight line forces the elements to twist, which they don't like. There's a length problem, and then they slowly snap into place. How to prove that this is working? So we tried to build a larger beam. So this one, we thought it would be nice if it spans 10 meters. The 10 meters come from the idea that if you have a plate that is 5 meters long, you also need to stitch in a tangential way. So you need to generate a large piece. So what you see in the upper line is the classical paper model. And what you see on the lower part is the sandwich that we are going to build. And you see there's already in the middle, there's one line. So there was like a way to see if that works. So how to actuate as things are very large. Yeah, it's working. I'm not sure if it has sound, but probably you can imagine how that works. So we put a screw in the middle, and by just shortening the distance between those two, we tried to see if that really works, that it snaps in place. And you see there's a moment then it snaps and becomes a stable configuration. So if you do that with a wood construction company, I have to thank Holzbau here in Austria. They allowed me to do this madness. So we built this large piece of wood. We pressed in some hinges. So here the hinge is just a cold deformed metal plate that we pressed in with some teeth. Then you close the sandwich, and you see you need some pieces that keep the plate from the self-weight that would bend through. So there's some additional parts that are required. And then you have the sandwich, and then what you see behind it is already one folded element. And then we tried to kind of actuate it. And the problem is you have to look here in the middle. There is like this angle that prevents the piece. So it moves very slowly, and it's very hard to know when it snaps. So this is really a frightening process. If you see that in slow motion, it's really like you don't know when it's happening. So this is the distance, so it goes. So it's very hard to predict when it will snap, and it's a very hard to control process. But you can fold. You don't need too much manual work in that case, and you can build a nice bridge. But still, we were quite unhappy that you have to do it by hand. There's no way to kind of push a button and make it work. So together with Markus Bernhardt, who is also here, we developed these kind of channels on a surface. So they work on a cone, on a cylinder, so you can easily place them. And if you have several of them, you have a motion and that you can finally block in some way. And what is interesting, by actuating them, you can bend the surface that is underneath. So what are you doing with those? So we thought you could easily fill it with some tube and let the element fold itself. Of course, you always do a very small testing first, and then, oh yeah, can work. So maybe we have not much ideas. We tried to do some beam-like element, but in that case, only a simple arch to see how that works. So basically, we thought you have something, you can have the handrails mounted. Try to work with the different hinge solutions. So this one is a textile strap. And then, thanks to the FFG, they sent the videographer and to the fireworkers. Oh, why is it stopping? Oh, no, it isn't. We could put in some fire tubes. Usually they're filled with water, but they can be easily, I don't know, it's stopping. There you go. So you can fold the thing and you can stand pretty far away. So there's no need for manual labor. You just have to put in these things and fill the cross section. And so, yeah, that's how you get this bridge beam, and then you fix the second border, and then you can have something like this. So yes, I guess I just give a sneak preview. We did a very large experimental thing. We tried to apply the quad filling algorithm to some piece of wood. We currently tried this out, having a very large one, just of 40 segments, 40 different pieces put together. And if you just squeeze it in the right way, you can build something like this. It's not yet published. We just show it at the IHF, and we will probably, if everything works perfectly, show it at the Forum Bois Construction in the Grand Palais in Paris in the end of February. And after 15 minutes, I'm done. Thank you very much.